thank you all very much for having me here today. And the title of my talk today is Our Revolving Sun, Life on Earth, and the Habitability of Other Worlds. So, if you're to go outside, maybe not in downtown Boulder, but go out into the mountains somewhere, or better off into the desert, and as you get the nice dark skies, you can look up, and the human eye can make out a few thousand stars from the naked eye. However, this is just a scant, trivial bit of the total. Our best estimates are that there are probably around 10 to the 22nd power stars in the universe. That's a 1 followed by 22 zeros, or in English, a 10 trillion billion. And what's even more amazing than that is we now know that nearly every star has planets. And why shouldn't they? 400 or 500 years ago, Copernicus proved that the universe does not revolve around humans, and that the Earth revolves around the sun, and our sun is just a common star. Why should our star and our system be any different from the universe at large? And well, it took us a long time, humanity quite a long time, to get the technological capabilities to actually detect planets around other stars. And thus far, in the past 2 decades, we are discovering a dazzling variety of worlds, planets that we wouldn't have been able to imagine otherwise, without actually detecting them ourselves. So, as of, I think I actually checked yesterday, not today, but on the NASA Exoplanet archives, there are 1,963 confirmed exoplanets, with several thousand more candidate planets. And just as a digression, the two main methods today that we detect these planets are shown here: radial velocity and transit photometry. Now, it's very difficult to actually take a picture of the planet, of these exoplanets, because the star is very large and very bright, and the planet is very small and emits very little energy. So it's trying to see the fly that's flying around a bright floodlight. All you see is the floodlight. So in the first method that we've been able to detect these planets is that it's the effect of gravity. Planets don't revolve around their star, but rather the two revolve around a common center of mass. So the planet, shown on the outer ring, actually causes the star to wobble just a little bit. And we can see this wobbling effect and deduce that there's a planet surrounding it. And now the other method at the Kepler Space Telescope, which is operated here at LASP, uses transit photometry, where you actually see the shadow of the planet cross in front of the star. It eclipses the star, and you see a dip in the amount of light that we receive in the telescopes. These are the two main methods of how we actually detect these planets. And as a further digression, our observational biases currently they favor the detection of large, close-in planets. So this is an older plot, but it's still, and it's a fast-moving field, but it still is relevant. There's the Earth, and you can see most of the points on this plot are this way towards closer in, or this way towards larger planets. And you can see the smattering of methods. The direct imaging method of actually taking a picture of the planet, you can only do it if you have a very large planet very far away from the star, so you can get a little bit more contrast. But without belaboring the point, you see most of the detections are as radial velocity and the transit technique by the squares. So, most of the planets we found so far are maybe hot Jupiters, which you've heard about, these very large planets, bigger than Jupiter, closer in than Mercury. Our detection biases favor their imaging, or favor their detection. But what I'm most interested in is finding the Earth-like planets, the habitable planets. So you may or may not have seen last summer, NASA had and Kepler had a big announcement that Earth's twin has been found, or rather, Earth's bigger, older cousin, Kepler 452b. I think this was last July that it was announced. And so some of the things we know about this planet: it orbits a sun-like star. It's just about the same temperature as our star. It's a little bit older in its evolutionary lifetime, but it's very close. We know this planet has a 384-day orbit, so getting pretty close to what we think about as an Earth-like characteristics. The combination of the star being a little older and with the orbit, we can deduce how far away the planet is. And we know that the planet receives a stellar flux that's 1.1 times that of the modern Earth. That's 10% more than the Earth receives today, which is, again, it's pretty close. Earth has been habitable over its lifetime, and the sun has varied by 25%. So what's another 10%? This is, close, very close. And then, as I mentioned, our selection biases make it so it's easier to detect larger objects. So this planet has a radius 1.6 times that of the Earth, and a planet mass about 5 times that of the Earth. So bordering onto the so-called super-Earth regime, but it still could be, very well could be a habitable rocky planet. So we have this beautiful artist's rendition of Earth's bigger, older cousin. It's got global ocean and ice caps and clouds and storms, and it's beautiful. But what we really know about Kepler 452b looks more like this. It's an orb in space. It's a sphere. We know its geometric properties and how much sunlight it gets. But we don't know what its atmosphere is really like. We don't even know if, firmly if it's a terrestrial planet. But so it remains a big question mark. Yes?
How many light years is it away from us?
That's a good question, and I actually don't know the answer. My field kind of crosses over between climate science and astronomy, so I'm very focused on the atmosphere, and then I confer with my astronomy friends, and they tell me the details as far as how far away these things are. I'm sorry I can't answer your question. But with that, in order to make these claims of finding the Earth twin, I'm sure most of you, if you're here tonight, you've probably seen the movie Interstellar, where we embark on trying to find another Earth, where after we've trashed our planet, we're going to go save ourselves. So first we have to ask, well, what defines a habitable world? And to do this, the first thing we do is we look closer into our own system. We know a lot more about our own solar system. And of course, we know the most about the Earth. The Earth is the only habitable planet we know. And water is the key to life. As far as we know, water is the key to life. So, when we look for habitable planets elsewhere, the first thing we're thinking about is an ocean-covered planet. The Earth is essentially, it is an ocean-covered planet. 70% of the Earth is covered by ocean. Water dominates the climate system. We're looking for planets that have widespread life. And thus, we're looking for an ocean-covered planet. But this actually provides a significant constraint on the surface temperature. Water is only stable as a liquid, thermodynamically stable as a liquid between a narrow range of temperatures. Might seem a lot for us, but in the scheme of the universe, the freezing point and the boiling point of water is a narrow range of temperatures, 100 degrees Celsius. And also, as I mentioned, water dominates the climate system and is the cause for 2, in particular, strong positive and negative climatic feedbacks, which influence climate and actually can drive the climate in the wrong direction towards chaos rather than towards habitability. So, a habitable planet is not a snowball Earth. This is a frozen planet. It's too cold to maintain conventional widespread life at the surface. And the action of the sea ice albedo feedback is to blame. So we all know snow and ice, it's white, it's very bright, it hurts our eyes. So if you have some initial cooling of the planet, this little circular figure here, you're going to end up having more sea ice. It's going to creep a little bit more equatorward. And the more sea ice you have, the more solar reflection you have, and so less solar radiation is absorbed at the surface, and the planet gets colder, and then you get more ice, and it gets cold, and it spirals away until you get a snowball Earth. So water is the key to all life, but it can also do dangerous things to the climate. The other way is a runaway greenhouse, which is also not a habitable planet, and this is water vapor in action. Water in its gas phase is an extremely potent greenhouse gas. So, likewise, we have a same circular feedback cycle, but this time in the warming direction. If you have some initial warming of climate, you end up getting more water vapor in the atmosphere. The atmosphere can hold a lot more water the warmer the temperature gets. And then with more water in the atmosphere, you get a stronger greenhouse effect. Then you get increased warming, and then the cycle goes on and on and on until the planet can spiral out of control and become far too hot for life to exist. So these two states, the runaway greenhouse and also the snowball Earth, can be considered runaway glaciation, bracket the so-called habitable zone. So, and somewhere in the middle here, fortunately, is Earth, where things are just right. So we define habitable worlds as those with abundant liquid surface water. However, that is not to disregard, there are some caveats, extreme niches for life that I will digress and mention because they're interesting in their own right. In the dry heat of the Atacama Desert, we found microbial life. There's almost no water, the driest place on Earth. In the boiling pools of Yellowstone, beneath 2 miles of ice in Lake Vostok in Antarctica, and a particularly interesting scenario which lies in the face of what I just told you is subterranean oceans and tidally heated icy moons of our gas giants. So Ganymede, Europa, Enceladus are encased in water ice, and they're very far out in the solar system, so they receive far too little energy to melt the ice. But tidal interactions, gravitational interactions with their parent planets, Jupiter and Saturn, can internally heat the planet. So our satellite measurements think that there's a subterranean ocean between the ice and the rocky core on these worlds. And we see from Earth that we have these things called hydrothermal vent communities, which are communities of life in the deep sea where they receive no sunlight and they get their energy for life from these black smokers underneath the sea. So it's very feasible that, these moons could be habitable as well. But for our purposes today, I consider these niche habitability regimes, because if, put yourself in the movie Interstellar or trying to find a new home, none of these are going to suit us well. So for our purposes, we seek broadly habitable surface environments with liquid water at the surface, such as this planet right here. So this brings us back to our favorite planet of the moment, Kepler 452b, and it's not just Kepler 452b, but there's currently, I think this is January 8th, about 40 exoplanets can be considered potentially habitable. These are ranked by Earth Similarity Index. I'm not exactly sure what that is, but the main point is it's about 40 candidates that could potentially be habitable at the moment. So how do we go about determining if any of these exoplanets are actually habitable, given that currently our view of them is still just orbs in space, perfect spheres, and we don't know anything about the climate? So the first thing we can do to determine if an exoplanet is habitable is, again, draw on what we know. And now what we know is our own solar system. By comparison, we know a lot about Venus, and a lot about Mars, and of course, we know a little bit about Earth as well. So long before we thought about the habitable zone and extrasolar planets, we thought about the Goldilocks problem. Why is Venus different from Earth, different from Mars? Or rather, Venus is just a little bit too hot, Mars is just a little bit too cold, and Earth, like the third bowl of porridge, is just right. So we're able to first draw upon our rich knowledge of our planetary neighbors. So let's first start thinking about Venus. Satellite measurements of isotopic ratios in the atmosphere of Venus indicate that Venus likely had water on in its atmosphere, maybe on its surface, in the past. And this also goes hand in hand with the fact that the sun was dimmer in the distant past. So was Venus cooler and possibly habitable in the distant past? And then as the sun brightened, it went into a runaway or a moist greenhouse. This is when as I explained earlier, the water vapor greenhouse feedback gets into an unstable loop, and the climate gets warmer and warmer and warmer. And then, which I'll explain a little bit more on this later, the water can essentially evaporate away to space. It gets eroded away to space. And all the oceans of the planet can leave the planet, and the planet becomes desiccated, a dry, barren rock. And then in the case of Venus, and in the case of any planet when you're going to lose your water as such, weathering processes stop, which can sequester carbon, and continued volcanism can build up a dense CO2 atmosphere. And that's what we see on Venus today. So Venus is actually not a runaway greenhouse, as I like to think about it, because I think of the runaway, I think conventionally, the runaway greenhouse, you think of water vapor greenhouse feedback going out of control. Venus is actually the aftermath of a runaway greenhouse. All the water is already gone, and now there's nothing left but CO2. And then, of course, there's the case of Mars. There's obviously a ton of attention that's been given to early Mars. I'm sure many of you have seen, all of you have seen the amazing pictures of all the water, the erosion features and the water features from Mars. So we think that early Mars as well might have been potentially habitable with water on the surface. Mars poses other challenges though, because unlike Venus, where you can say, well, the sun was less dim, or the sun was less bright, it was dimmer, there was less energy, maybe it was cooler, maybe this can work. Mars is a worst case because it's further out and the sun was extremely faint, especially early in its history. And actually I encourage you to come to our next week's talk about the MAVEN mission. And the MAVEN mission, headquartered out of CU and LASP, has shown that Mars' atmosphere has actually slowly eroded away because it doesn't have a magnetic field, and its atmosphere is just slowly stripped away by the solar wind, so it never even really had a chance to enter into a snowball Earth, a sort of snowball planet generically, as it lost its atmosphere. And today, we see Mars has almost no atmosphere, very, very thin atmosphere, and is certainly, well, not conventionally habitable. So, and then finally, of course, Earth. Earth, we love Earth. Earth is nice and habitable. It's our favorite planet. Earth has been continuously habitable for virtually its entire lifetime, despite the sun having increased in brightness by 25%. So this is a pretty significant change in forcing. Yet the Earth has been able to regulate itself to maintain habitable conditions for billions of years, which this is a very good thing because it took humans, 4.5 billion years minus a couple million to get here. So you need a long-term, as far as we know, a long-term stable habitable climate to produce life. Of course, I'm going to contradict myself for a second, and in the geologic record, we actually have record that there might have been numerous snowball Earth events where the Earth became almost completely or completely frozen in ice, as recently as the Neoproterozoic, which is about 450 million years ago with the last snowball Earth event. But each time, the Earth was able to recover and return to its nice habitable state that we enjoy today. And another problem that is unavoidable, really, for the future is that the sun will continue to brighten in time. And this is going to make the Earth continue to get warmer. Even if we brought CO2 to zero and all other non-condensable greenhouse species to zero, you would still have this water vapor greenhouse feedback that is going to take into effect. It's going to warm Earth. You can lose water to space, just like happened with Venus, and then Earth will desiccate and may likely end up looking like Venus again one day. One day well, it depends upon your scale of time. Numerous models predict this might be happening in about 1 to 2 billion years, so you don't have to get worried about it, but 1 to 2 billion year time frame, that's about the time frame that humans are going to start needing to look for another planet if we don't kill ourselves otherwise, or we don't get hit by a meteorite. So just keep that in mind. So habitability, we can say, is inextricably linked to the evolution of the host star. The host star brightens over time. Water climate feedback, so the water vapor greenhouse feedback and the CA-albedo feedback. And also the presence of other greenhouse gases. I'm mainly thinking about CO2 right now. Methane could be another thing to think about, but mainly we're thinking CO2. So what we've done here is we're trying to draw on our rich knowledge of our planetary neighbors, but we're still missing some pieces because we have slices in time from these planets, and we're trying to put together the pieces to understand the processes of the atmosphere and how these planets evolve. So when we think about our orbs in space, how do we connect these pieces together? Well, we use numerical climate models. So this is my expertise. I use three-dimensional general circulation and climate system models. I use a model that is curated by the National Center for Atmospheric Research right up on the hill off in South Boulder. And so we take the NCAR models and we try to adapt them to these unusual problems of climate, extreme climates, exoplanets. And this is, so for years and years, these problems have been handled, but there's been an evolution, of course, with the models from zero-dimensional, just simple energy balance models where you just have simple equations trying to figure out, well, what's if we can categorize this whole place by one single value of a temperature, what is it? And then the next evolution was one-dimensional models, which are just, it's just assuming the entire planet is one spot on the Earth and then one column of the atmosphere that goes all the way to space in an average sense. Well, what does this tell us about it? But now we're at the point with our computing skill and power where we can consider the full planet, the winds, clouds, ice, radiative transfer. So, climate is complicated. It's very complicated for the current Earth. It's also complicated for these types of problems as well. So, in a general sense, figuring out the climate is about balancing the energy, the incoming energy with the outgoing energy. So the sun provides the energy that's going to enter the planet. And that energy can be reflected back to space by clouds in the atmosphere. It's reflected by the surface. Some of it gets through and absorbed by the surface. We also have the water cycle where energy reaches the surface. It evaporates water, it goes into the atmosphere, it releases its energy elsewhere, it forms clouds. The energy from the sun drives the general circulation, which is dictated by the rotation rate of the planet, and determines where the clouds are, where the storm tracks are, which all affect how reflective the planet is, how much solar energy comes in. And then on the other side of the equation, we have the outgoing energy from the greenhouse. We hear about the greenhouse effect. The thermal energy that leaves the planet, and then greenhouse gases like water vapor and CO2 can trap that energy in and radiate it back to the Earth. Some escapes to space. Clouds, some high clouds can also contribute to this balance. So climate is complicated. So to get these problems right, we really need to use sophisticated three-dimensional models of climate to consider them. Up until there was a seminal paper from 2013 for defining the habitable zone, which has been cited hundreds of times already, and they use a one-dimensional model and they ignore clouds, they ignore sea ice, they make a lot of gross assumptions. So now the next step is to go from there and apply our sophisticated three-dimensional models of climate in order to determine habitability. So we can determine the habitability by synthesizing our knowledge of the Sun, Venus, Earth, Mars with our 3D numerical model. So I mentioned a bit about our Sun, our evolving star, the Sun. And here's a nice image from the NASA Solar Dynamics Laboratory. The Sun is a very dynamic entity, but it is a very common star in the universe. So this is, if you're familiar with the Hertzsprung or Russell diagram, showing all the different types of stars that we see out there. And we'll focus on the main sequence stars. You can think about these as your stable, responsible adult stars of the universe. But even so, these bluer stars, they don't live long enough to really make good candidates for life. As the old cliche statement, the star that burns twice as bright lasts half as long. So some of these larger stars have lifetimes on the order of tens or a few 100 million years, and it's just too short. Humans, we took 4 billion years to get here. So what chance do they have there on these rapidly evolving stars where they'll die off in 100 million years? So our focus is towards these. So those aren't good candidates for finding these habitable worlds. So we focus on the cooler stars, which our Sun is one of them, right about there, because our Sun can live for about 10 million years. As you get into some of the cooler stars, they can live for 100 billion years. They have nice stable lifetimes that we can find planets. And we would expect that to be enough time for life to evolve. So, thinking about our sun, this is a schematic of how our sun evolves. So we know the main sequence stars gradually brighten over time. So here we are now about halfway through the sun's lifetime. It was dimmer in the past, and it's slowly getting gradually brighter and brighter and brighter. And then about 5 billion years from now, it's going to enter its red giant phase, where it's going to expand, exhaust all its nuclear fuel for burning, and expand outwards past the radius of Earth. So if nothing bad happened in the meantime, this is really the end game for our system. But, so theoretical calculations of stellar evolution, which is what I show here. This is the age of the star, this is for the sun, with the ratio compared to the brightness of today's sun. So just focus on the solid lines, the solar luminosity. So here's the present day right at the intersection here. And so during the Archean period, this is the earliest period of, well, I guess I should say the second earliest. The Hadean came before the Archean, but this is the earliest habitable period of the Earth's history that we tend to think about. I know I have geologist friends who would argue and say, no, there was microbes in the Hadean as well, but this is when we think life really started to get going. And actually, at the earliest part of the Archean, the sun was about 25% less bright than today. That's a significant fraction. And just to put it into context, we think about carbon dioxide today and anthropogenic climate change. Doubling of CO2, which would kill. It's a lot. That's a large change in CO2 for anthropogenic standards, equivalent to about a 2% increase in the solar constant. And here we're talking about a 25% decrease. And if we go into the future, things get equally scary, but in another direction. In a billion years, the sun is going to be 10% brighter. To about 2 billion years, 20%, and about 4 billion years, it's going to be 50%. So, we can say that the natural evolution of main sequence stars has a profound influence on habitable world, just sheerly by the sun drives our planet, and changes in the luminosity of the sun obviously are going to have a huge impact on our planet. So, first let's talk about the fate-young sun paradox. Well, what is the fate-young sun paradox? As I just mentioned, early in the Earth's history, you had a reduced solar luminosity, yet we have geologic evidence for a warm, maybe even very warm surface, abundant liquid water, and also primitive life. And this is relevant not just for early Earth, but also for early Mars. We think that they both had liquid water at the surface despite weak solar energy. Earth at towards its earliest periods, had about 75% of the modern solar energy. So a 25% reduction, 75%. So Mars is further away. So early Mars maybe had around 44% of the modern solar constant we receive at Earth. So the problem for Mars is much more dire. So for Earth, I found my one typo for the day, hopefully. If Earth's atmosphere were the same as today during its history, the planet would have been frozen solid for much of its history. So in this plot here, we have the age. The age from the present day is right here. And this is billions of years ago, and this y-axis is temperature. And this is loosely the actual temperature that we have. It's been more or less stable. This line highlighted here comes from simple 1D calculations. It's the temperature expected on Earth if the atmosphere never changed. So if you have the same atmosphere, the same amount of carbon dioxide, what would the temperature be? And we see that this is the freezing point of water. The Earth would have been frozen over for its first several billion years of its history. That flies contrary to all of our geologic evidence. So fortunately for Earth, we can go around and we can dig into the rocks and dig into the ground, and we can find constraints for what the environment and the CO2 was. in the distant past. So this, don't worry about the details. You have time before present and amount of CO2. And there's a variety of studies, and surely there'll be more, trying to constrain the amount of CO2 in the past. But it was surely above the present atmospheric level. So that's good. We can get more, we can counteract the young sun by having more CO2 in the atmosphere. So one of the faint young sun paradox actually has a long history of back and forth between the geology communities and the climate science communities. And over the past decades, it's actually kind of finally come to it. There's been a lot of ideas that have been thrown back and forth, and we've finally gotten to the point where the ideas from both communities are starting to merge. So our most recent geological estimates on CO2, we can plug into our most advanced climate models, and we get reasonable answers that show that for Earth it's not really a paradox, that the numbers actually, what the geologists are finding and what our models are telling us actually work out pretty darn well. So here, this is some calculations I did as a graduate student for the Archean climate. So you have the amount of CO2 along here, and then the temperature of the planet along here. This first line has no methane, and we see, okay, this green line right up here, I guess you could say is a late and great constraint on CO2 that we have. If we use that value from Dries et al., 2011, we get a temperature in our model of about 270 Kelvin, which is just on global mean below the freezing point. But the whole planet isn't a snowball. You actually have large ice sheets that cover down into mid-latitude. It's a severe glacial period, but you have a broad, warm, relatively warm ocean that covers 60–70% of the planet in this state. And then if you add in a little bit of methane, this is the next kicker, an acceptable level of methane from the best of our knowledge, you can get the temperature back up to close to the modern day. So really, the faint young sun paradox of Earth is no longer a paradox, because the numbers were what the geologists tell us and our models tell us and the chemists tell us about the greenhouse gases, and they come together in a nice tidy picture. So, one interesting thing about methane, we do, as I pointed out in the last slide, to get from a kind of a chilly Earth to an Earth that's very comfortable like today, you do need a little bit of methane to augment your CO2 based on the CO2 constraints from geologists. And this is perfectly acceptable because of early life, actually called methanogens. They actually respired methane back into the atmosphere. And the early Earth had no oxygen. So the lifetime for methane, today oxygen chemically can destroy methane in the atmosphere. It's a very short lifetime. But in the Archean, without a lot of oxygen, methane could have built up to large concentrations. And then the next caveat is that, well, if you have enough methane, you can start forming these Titan-like hydrocarbon hazes. This is a picture of Titan's famous and ubiquitous hazes. These do a lot of interesting things. They can cool climate, but on an early Earth with no oxygen and no ozone, the surface environment may have been strongly irradiated with ultraviolet radiation, harming the life on the planet. So these hazes can actually also provide an ultraviolet shield and kind of a Gaian feedback that the methanogens produce the methane, and the methane caused the haze, and the haze protected themselves from the ultraviolet radiation. So this is kind of a neat thing that's still being looked into at the moment. And then finally for the Earth, there's also a few other things that can make the planet even warmer. The early Earth probably had very little emergent continents. So generally speaking, the ocean is darker than the land. So it would absorb more energy, and so you'd have a reduced surface albedo. Without getting into the details, there's some plausible changes to how the physics of cloud droplets from the distant past that would have made the clouds, the lower lying clouds, a little bit thinner and allowed in more energy. And there's also a at this point maybe also a controversial notion that you could have had an increased amount of atmospheric nitrogen on the Earth that's been slowly drawn down. Others say the opposite, so that one maybe put a caveat by that one. But there's other mechanisms as well to warm the Archean, so when you start putting all the pieces together, it's really not hard to get a warm early Earth. Do you have another question? I guess not. And so, for Mars, The problem is much more difficult. As I said, it's further away from the sun. So when the sun was 75% as bright as today, Mars was receiving actually about 44% of what the Earth receives today. So our models, this is actually a 1D model from Ramirez et al. Shows that CO2 alone cannot warm early Mars. And you know, I know I'm showing a lot of plots. I'm hoping I'm doing an okay job at describing them. So just focus on the circled region here. So you have the surface pressure for this is the CO2 atmosphere, and then your temperature. And then for these values, 0.8 and 0.7, this is the early history of the sun. And what you see is you can never have enough CO2 because as the sun is so faint, and as you build up CO2, the atmosphere becomes thicker, and the molecules themselves begin to scatter away the solar radiation at a rate that's greater than the CO2 can actually trap in the greenhouse gases. So you can't just say, oh, well, Mars is warm and had, 10 bars of 10, atmospheres of CO2. That doesn't work. It doesn't work. You have to look for other methods. So numerous things have been postulated. There's a paper that SO2, greenhouse from SO2 could do this, but no, you form sulfate aerosols like you do in volcanoes and it reflects away, or like in geoengineering propositions, you reflect away more solar energy than you gain from the greenhouse. Methane is a great greenhouse gas, but you got this haze problem. Some research I've been involved with lately about the early Earth shows that you can probably dangle right on that line of having a haze that's just thick enough to do some good with UV, but not quite thick enough to cool the planet catastrophically. But with Mars, the sun is so dim that you'd have to have a ton of methane, and then you'd end up with very thick hazes, which would cool the planet and negate its greenhouse potency. Another idea that was posed is maybe you had a hydrogen-rich early atmosphere, but this poses a number of problems. And, well, how did the hydrogen get there, and how did it stay, especially since we know Mars' atmosphere is eroded to space, and hydrogen is the lightest element, which is most prone to escape from the atmosphere. So it's been proposed and theoretically shown as climate model calculations, but it's not clear that it's actually realistic. Another thing that was postulated is maybe, well, you have global cirrus clouds. Cirrus clouds are those very high wispy clouds that you see. They don't reflect a lot of sunlight, but they actually can trap in long wave radiation quite well. And so they've been theoretically posed, but our cloud models are uncertain, and so it's not clear that this is really a viable solution either. And so one of the ideas that actually my advisor Brian is a big proponent of is the impact hypothesis theory, that maybe these river patterns, these erosion patterns, were from catastrophic events or brief events where a big impactor hit Mars and injected a lot of water into the atmosphere, and that water condensed out and rained out, and causing these episodic instances of water features on Mars. And so this doesn't require early Mars to be terribly warm. And actually there's a very recent modeling study which, I don't think they talk about the impactors, but they argue a similar notion that Mars was never warm. Mars was always cold. And that you actually had you didn't have a warm planet with oceans, but it was always cold and icy. And then some periodic mechanisms would cause periodic melt flow to cause these features. So, for Earth, the faint young sun paradox, I may be so bold to say that it is essentially solved. I mean, it's not really a paradox anymore. For Mars, the problem remains. It's a tough problem. I don't think there are any of these theories that I presented to you. I don't think any of them have been glommed onto by the community as the one true theory to rule them all. So, the next thing I'll talk about is moist and runaway greenhouses. This is a topic I personally like it. I think it's very interesting. But so as the sun will keeps increasing its luminosity over time, the sun will get brighter, the Earth will get warmer, brighter, warmer, brighter, warmer. and that water vapor greenhouse feedback until we can start losing water vapor to space. I kind of skimmed over this pretty quickly, but what happens is if you get enough water vapor high in the atmosphere, it can actually start breaking apart. So a solar photon will come through, break water in half. This OH is very reactive. It'll react with something, go back to the system. The free hydrogen will escape to space because it is so light. And thus we've lost a water molecule to space because you need hydrogen to make water. And if this process happens rapidly enough, you can lose the entire ocean to space. So we took our 3D climate model and we did some simulations on what's going to happen when the sun gets brighter. So here we have temperature, the global mean temperature of the Earth on this curve. And this is climate sensitivity. It's essentially, it's a measure of how reactive, maybe that's a good word, the climate is to a given change in the solar input. So we see right now we're on this temperate branch of climate. We're right about right here. Things are nice. And even as the sun gets brighter up to about 11%, it gets warm. You know, obviously there'll be chaos on Earth as far as humanity's involved. And we get up to 310 Kelvin, which is quite a bit warmer than today. But the way the climate behaves, the way the clouds are structured, the way where radiation and convection are occurring are similar enough to the Earth today that this is one regime of climate. Then you can probably see where I'm going. There's a sharp transition region. You get to a certain point and boom, the climate jumps up into this next phase of climate. We call it the moist greenhouse, which, so there was a study not a few years back that says that human life, if we don't evolve at all, the human body will essentially physiologically fail when you get global mean temperatures right towards the upper end of this temperate region. So once you get into the moist greenhouse region and it's 330 Kelvin, it's too hot for humans physiologically to survive. Maybe by then, that's in about a billion and a half years. Hopefully by then we'll have evolved somewhat, maybe stop killing each other with wars and whatnot, and we'll also be able to deal with very hot temperatures and things will be fine, but we can't count on that. And regardless, even if humans are able to adapt in the long term, once you get to the far right of this curve, you start getting into the significant water loss regime, where as I mentioned, the Earth will eventually start blowing off its water to space, and the planet will start drying out. So, without delving too much into the nuance, the difference between the terms runaway and moist greenhouse. In a runaway greenhouse, that water vapor greenhouse feedback spins out of control. The planetary energy is critically imbalanced. We're taking in so much more energy, the planet can't shed it. The surface temperatures skyrocket to the most recent of calculations say maybe about 1600 Kelvin. The planet is sterilized and all the water is lost, and there is no hope. So for the moist greenhouse, the key is different because the energy balance is always maintained. You don't enter into this runaway process. The climate gets a little bit warmer. It steadily warms, but it doesn't critically become out of control. And when the temperatures get into this, I know it's at and above the boiling point of water for 1 bar atmosphere, but you would still have oceans as the water is being lost. And the planet is not fully, you can argue the planet is not fully sterilized. So, now that we've talked a bit about early Earth, early Mars, and also the future of Earth, we've also talked about Venus. This kind of brings me back to the original point of, well, how are we about the habitability of other worlds? So we try to, we're first looking for Earth-like planets. So we take these concepts which I reviewed about how did the Earth stay warm despite having very little sun? How is the Earth going to react with a lot of sunlight? How did Venus evolve? How did Mars evolve? We try to take these concepts and apply them to what we're finding in the universe. But there's some extremely interesting things about the habitability of other worlds that we're finding, which are, we don't have an analog for in our own system. And one of my personal favorite of the moment is tidally locked planets around M dwarf stars, where you have the same side of the planet always faces the star. So you see this little guy here. And this is like the moon, the Earth and the moon. The gravitational interactions between the Earth and the moon means the same side of the moon always faces the Earth. So, for these M dwarf stars, which are the smallest and most common star in the universe, as we see, here's our sun, here's a blue dwarf, here is a star right here, I believe, is the largest star ever found in surveys. Then you got the red dwarfs over here, these little guys. They don't emit that much energy. And thus, for a planet to be in the habitable zone, to get enough energy just to melt off the ice, it has to be very, very close in to the star. And thus, it becomes embroiled with the gravitational tidal interactions and becomes tidally locked. So just like the moon and the Earth, one side always faces the star. So you end up getting these really weird climates. So here's a schematic. One side is always daytime, and the other side is always nighttime. So if you live on the night side of the planet, it can be really, really cold and icy, while on the day side of the planet might be a habitable region. And what's really interesting about these problems is you can't simulate these type of planets with your simple 1D models or energy balance equations. So you need to use 3D models to simulate these planets. So here are a few, thought I'd throw in some movies to spice it up a little bit, maybe wake you up. You take your model and comparing Earth to this eyeball climate state. So here's our Earth-like climate. You can see this is temperature. It's warmer at the equator, colder at the poles. And even though this is a coarse resolution simulation, you can squint and look at the clouds here and convince yourself, oh, there's tropical, there's the tropics. You got all, tropical band of clouds there, and in the mid-latitudes, you got storm clouds rolling through storm tracks. And then when you see the eyeball climate, it's completely different. The day side, the sun is always shining here, and it's always dark on the backside. So it's warm underneath the sun and cold on the backside. And what's really interesting is how different the clouds are. As you can see here, this region ends up to being in the perpetual tropics. So you've got this perpetual tropical convection going on right here. So you get these thick clouds right at the substellar point, as it's called. So this is, and actually the rotation rate of the planet matters. So you can kind of see the evolution from a slower rotation rate moving to faster rotation rates. But still, you have these thick clouds right where the sun is shining. So this actually, you can think about it, it's like a pair of sunglasses for the planet, that it reflects so much radiation, solar radiation, that you can move these tidally locked planets much closer to the star than you would have guessed if you had just used a traditional one-dimensional model because of this unusual cloud pattern. Another topic that I hope to get to start doing some research on is habitable desert planets. So, as I mentioned for Earth and for Venus, you can lose your water to space, and if you do so in a moist greenhouse, not a runaway greenhouse, you can desiccate the planet, but recall that in a moist greenhouse, the loss of the oceans can occur without planet sterilization. So, on a dry planet, I mentioned for the runaway greenhouse, is the water vapor greenhouse feedback gets out of control and makes the planet too warm. Well, if it's a dry planet, imagine your favorite sci-fi desert planet, whether it's Tatooine in Star Wars or Arrakis in Dune, that you have very little water, so you don't have much greenhouse effect from the water. So you can actually move these desert planets much closer into the star too. So, here we go. You can have these desert planets which are much closer to the star, like where Venus is now, and as long as it never had a lot of water, or it lost its water in a just the right timed fashion, you can have a desert planet with some water ice at the poles. It remains habitable much closer to the star, and it's somewhat Mars-like, but just much closer to the sun. And if you needed a magnetic field to protect the atmosphere being stripped away, but these desert planets may be more robustly stable than water worlds. Of course, they're probably not as robustly habitable as water worlds, because water is so scarce, you'd have to go and find it. So, lastly, the main, trying to synthesize a lot of topics here. And the main hot button topic at the moment is the so-called habitable zone, about where in space could we find, when we find these exoplanets, where is it just right to find Earth-like planets? So I will leave you with a very recent figure summarizing, there's a lot going on here, summarizing the different habitable zone calculations at the moment, from one-dimensional models, 3D models, there's a few, that's a desert planet in there, some more 3D, and a bunch of observations as well. So it's a complicated picture. We're still trying to parse out what exactly makes a habitable world. So thank you very much for coming to the talk today. I appreciate you letting me speak.
Are there any questions?
You said something about having a runaway effect once the ice melts. If we're able to melt our polar ices in the next 50 years or 100 years, is that going to trigger an increase, a constant increase in the Earth's temperature?
No, I mean, it's not to gloss over the dangers of melting the ice caps. It's extremely unlikely that you'd be able to, short answer, no.
Okay.
Numerous calculations have shown you need to burn like way more carbon than we even think exists in our reserves to do so.
Okay.
So, yes.
I saw an interesting paper a day or two ago on Science Daily, if you're familiar with that, and it was about the moon keeping the Earth's core molten.
Huh.
So we had, it's a wonderful thing. I said, oh my God,
Yeah.
because we've assumed the Earth to be much hotter in the past
Right.
to get to where the core is today, but the evidence shows that it wasn't that hot. And so these guys did, if you look it up on Science Daily, you find it, so that no one's taken account of the moon, and the moon, you know, the tidal forces and all that, have kept the core molten, so we get a dynamo, we get a magnetic field.
Right.
Therefore, if you want to find life, you got to look for a double planet out there,
Huh.
perhaps.
That's pretty, I'm going to bring that attention to my astronomer friends. That's a pretty interesting point. I'm going to look that one up.
Yeah, and our present exoplanet finding techniques, we can't discern whether you got a big moon. Am I right?
Right, that's correct.
Yeah. Otherwise, without the moon, we would have frozen out. Venus doesn't have a magnetic field? Or does anyone know?
Not sure off the top of my head.
No, Venus doesn't have a magnetic field.
And Mars doesn't. And
Mars
has a moon to keep, a big moon, right. So that really was a light bulb when I saw that.
Yeah, no, thank you for bringing that to my attention. I'm going to definitely look that up.
Mercury has quite a large magnetic field.
Oh, okay.
So you have these desert planets?
Yeah.
So couldn't you have like the opposite of desert planets? So they're like far away from the sun, but they have a lot of water?
Yeah, well, so that, with the desert planet as well, you can think with Mars. Mars is essentially a desert planet. If it had a little bit thicker atmosphere, it could also be more robustly stable because you wouldn't have more robustly habitable in the sense that you wouldn't have enough water to create the sea ice albedo effect and freeze the planet over. So the desert planet is an interesting opportunity because it actually, you avoid these feedbacks from water and you can make the planet closer in or further away while still technically being habitable. Yeah.
What about ammonia-rich world instead of water-rich?
That's that was a very popular idea that's been bantered about for a lot of people like to try it, and I as well was hoping that might work for the early Earth, but ammonia is very unstable photochemically, so people have tried numerous photochemical calculations and nobody's been able to get ammonia to stay stable at a high enough concentration in the early Earth's atmosphere to maintain. That was, I think, Carl Sagan's early idea that he'd have Miller-Urey experiment, an ammonia, methane world. And just nobody can, it's so attractive, but nobody can quite get it to work. So, any other questions, or you guys gonna let me off the hook easy? I don't mind getting let off the hook easy. It's okay. Yeah.
So for the one side, for the planet always facing the sun, you mentioned there would be lots of clouds.
Yes.
And I can imagine the temperature would be high because lots of energy goes in. But how do you think of the visible sunlight below the cloud? I would say temperature is high, but still dark, right?
So in our calculations thus far, and there's also, that's from one, we need more model comparisons, so that's with CAM, obviously, as you know. A similar calculation's been done with the NASA GIS model, which they get the same feedback, that you end up getting, it's thick convective cloud decks form, because you have constant sun on the one spot, and the clouds have a near ubiquitous cover over the substellar point where the sun is shining. So it's, the albedo of the planet becomes, what's the albedo of Earth, like 0.3 right now? It doubles, it's about 0.6 because the sun is always shining on this one spot. And as you're constant convective churning and constant convective water clouds. So for CAM at least, we can, nearly double, well, it's right here. Here you go, this is for CAM. This is a CAM 3 calculation. You can see for slowly rotating planets and then rapidly rotating planets, sorry, is right here, slowly rotating planets right here. And that's you can push this planet much closer into the star. This cloud is so thick. But as you know, cloud modeling can be uncertain, so it's exciting that the NASA GIS model duplicates this as well, but more intercomparison is needed, for sure. Yeah.
So for someone else, or?
Oh, you go first. Yeah.
So for the exoplanets we're looking at now, can we determine what the rotation is, or I don't know anything about this?
As far as I can tell, no. But the caveat is for these tidally locked planets that their rotation rate is the same as the orbital period.
Right.
So if we can get the orbital period, because we see that signal, the eclipse every time it rotates around, and with Kepler data, so thus we can know its rotation rate because it's the same as its orbital period.
And how do we assume that it's tidally locked?
I would refer to the experienced dynamicists of the bunch, but it's the same interaction of the. Well, I can't give you. It's outside of my realm of expertise, so I can't give you the technical rundown. But it's the same as the Earth, the Sun, the Moon being tidally locked with the Earth. We know that the M dwarf stars are so dim that the planets have to be so close to the star that they get tidally spun down. So, yeah, here.
Yeah, so the idea that the stars are warming over time, so this habitable zone is moving, is really quite interesting.
Yeah.
Have people talked about this, sort of this wave of runaway greenhouse going through a solar system, and maybe you could look, if you have an older star, you could see these dry planets on the inside and with the water and then ice. Yeah,
the idea is out there of the continuous habitable zone, and that idea is out there as far as the evolution, and it's slowly getting pushed outwards and outwards.
We're nowhere near it yet, but it'd be an interesting observational check on the runaway greenhouse idea to see if we see older stellar populations that have bleached.
Right. No, totally. And one thing I didn't mention as well, that I stress these M dwarf stars, and one of the reasons, well, they're very interesting in their own right in the physics that's going on, but they're also the planets that is most easy for us to detect planets around, the stars that's most easy for us to detect planets around, because they're small, they're dim, and thus the signal of the planet versus the star is more favorable for us. So I think you had your hand up first.
Are there any theories or evidence that any possible large life forms could have existed on any other planets other than Earth, or exist currently?
I would like to think so, but I'll just speak for myself. And the universe is so vast, and there's so many stars that it seems folly to think that there's not somewhere. But that would be a revolutionary breakthrough that the SETI program and a lot of our hunt for the Earth twin planets would love to find. So, yeah.
So the NASA Astrophysics Division is in the process of formulating studies of potential future what they call flagship missions. And one of the 4 that they are actively studying is called the Habitable Exoplanet Surveyor, I believe is the name of it. And this is viewed as a a major flagship class mission, bigger than Hubble and James Webb and things like that. If you had some input into it, you had your preference, what kind of observations or what kind of data of potentially habitable exoplanets would you like to see?
Well, that's a tough question. I think unrealistically, I would love to have direct image, Earth-sized planets in the habitable zone. That seems like a bold statement. So I would just say, just good spectral data. Good spectral data, so we can parse out the different constituents of the atmosphere. And actually, as another point that some of my astronomer colleagues brought up to me that I thought was interesting. It's really surprised me, but maybe you guys will find it surprising as well. So we're looking for water, follow the water. But the paradox is if you find water in an exoplanet atmosphere, that means there must be so much water in the atmosphere, so high up in the atmosphere, that the planet is in a runaway state or in a moist greenhouse state. So it's somewhat of a paradox that if you find water in a transit spectra, that means there's too much of it already. And so it's, I don't know the answer to that one. It surprised me, but anyways. Any more questions?
This is sort of a joke, but it occurred to me that one way to determine if there was intelligent life for another world from spectra would be what kind of spectra would you get from a lot of plastic in the ocean?
That's an interesting one. I know I've seen some papers talking about detecting ocean glint on different planets and whatnot. And I guess that's another point of what if you can parse out which, like maybe you found a bunch of CFCs in the atmosphere, in the spectra, or something like that. They're spraying aerosol cans up in the sky. So
we were laughing when they.
That's what they're seeing for us.